We present Self-Supervised Superplane for Neural 3D Reconstruction, which focuses on indoor scene reconstruction from RGB images. We aim at improving the RGB-based reconstruction results on textureless regions without any 3D ground truth annotation or implicit supervision from assistant networks. The key idea of our approach is simple. The constructed results provide a free geometric cue, the surface normal, which can be used to guide the reconstruction process of planar regions. Specifically, pixels belonging to parallel planes tend to have similar normal directions. Therefore, we group pixels sharing similar normal values into the same cluster, which we call a superplane, and force normal directions within the same superplane to be consistent. We use sphere tracing to improve the speed of superplane segmentation and employ iterative optimization between surface reconstruction and superplane segmentation during training. The results show that our method can significantly improve the reconstruction quality of planar regions and obtain the results of planar segmentation as a byproduct. Given multi-view posed RGB images, we aimed at reconstructing the surface geometry of the scene. This task has numerous applications in autonomous driving, virtual reality, robotics, etc. Traditional methods use multi-view stereo pipelines to solve this problem. Recently, however, neural implicit representations have gained much attention and have shown impressive reconstruction results without 3D supervision. For example, News and Vol SDF use an SDF to represent the scene and encode the scene into lightweight MLPs. Then, they render the image by volume rendering. However, these methods struggle to handle textureless planar regions that widely exist in indoor scenes. This is because they purely rely on photo consistency to construct the scene, which leads to texture geometry ambiguities since there are different plausible interpretations to satisfy this objective. Several recent approaches address this problem by introducing additional priors obtained from trained models that can be considered as assistant networks. For instance, Manhattan SDF introduces the Manhattan assumption on the floor and wall regions, which are predicted by a semantic segmentation model. NURIS and MonoSDF adopt additional normal supervision acquired from normal prediction networks trained on large-scale labeled datasets. Although these methods can regularize the reconstruction process on indoor scenes, they all rely on large-scale annotated 2D or 3D datasets. In addition, these pre-trained geometric prediction networks are sensitive to different scenes and not friendly across different domains or datasets. Therefore, we propose a novel neural 3D reconstruction framework with the self-supervised superplane constraint that can improve the RGB-based reconstruction results on textureless regions without any implicit supervision from assistant networks. As aforementioned, we use rendered normal map to generate superplane. In the bottom left figure, we show the rendered normal map and the corresponding scatter plot of the normal direction. We can see that, despite some noise, points belonging to parallel planes usually have more similar normal directions compared to others. Therefore, we group pixels with similar normal values into the same cluster, which we call the superplane. The superplane constraint is then applied to force the normal directions within the same hyperplane to be the same, thus constraining the reconstruction of large superplane regions. As shown in the bottom right figure, after applying the superplane constraint, the normals of different superplanes are more easily separated, which means they are pushed closer. Compared with using ground truth plane annotation or planes predicted by a pre-trained plane segmentation network, our superplane does not need any annotation and achieves better performance. This is because our superplane is typically larger than vanilla planes, thus providing more stable and accurate average normals when limited pixels are sampled in each iteration during volume rendering. Then, we will describe how to generate superplane more specifically. First, we use sphere tracking to generate the normal maps for clustering, since it is much faster than volume rendering and we need to generate normal maps for all training images. Then, on top of the normal map, a mean shift algorithm is used to obtain the superplane, since the total number of planes is uncertain at the time of grouping. With the obtained superplanes, we estimate the superplane normal by averaging normal of pixels belonging to the same superplane, and then enforcing all normals in the same superplane region to be the same as the superplane normal. The core idea of our superplane constraint is to enforce a global constraint on pixels belonging to the same superplane. However, since unsupervised superplane segmentation may include some noisy results, which may be non-planar regions or misgrouped pixels, we propose two strategies to deal with noisy predictions. First, we propose a self-guided automatic filtering strategy to filter out these outliers. Specifically, we compare the normals of all pixels in the superplane with the average normal and filter out all pixels whose normal direction differs from the average normal by more than a threshold value. In addition, we also directly mask out non-planar edge regions. Typically, these regions will have more color and geometric discontinuities. Therefore, we calculate the color and normal discontinuities for each pixel and mask out pixels with large discontinuities. We adopt an iterative optimization between the surface reconstruction and superplane segmentation. Through this training process, better reconstruction results bring better segmentation and vice versa. We performed ablation study on ScanNet. Quantitative results show the effectiveness of each component of our method. These qualitative results show that the quality of the reconstruction can be greatly improved with the addition of the proposed superplane constraint, as the ambiguity caused by the lack of texture can be resolved. We also analyzed the effectiveness of using superplane instead of ground truth or our predicted planar segmentation. It can be seen that the proposed superplane constraint can better recover the structure of small planar regions, such as sofas. Then, we show that the reconstruction quality of thin edge regions can be improved by adding 2 segmentation noise reduction strategies. We compare our method with other SOTA methods, and the results show that our method achieves the best performance among all methods without assistant networks, while being on par with methods that use additional normal supervision. Qualitative results show that our method can construct smooth and complete structures in both large and small planar regions compared to other methods. Finally, we compare the planar segmentation results of our method with the supervised method plane RCNN. The results show that our method produces more accurate segmentation results in the edge regions than plane RCNN. In summary, we propose a superplane constraint for neural implicit scene reconstruction without any assistant networks. And the generated superplane segmentation results can be further extended to unsupervised plane reconstruction, which can be used for auto-labeling. Experimental results show that our method significantly improves the reconstruction quality of textureless planar regions. Thanks for your listening.